Okay, welcome everybody. Welcome back to Behavioral Consumer Analytics. We will continue talking about demand estimation now. If you remember, we've been talking about the motivation for demand estimation, and this has been quite straightforward that if you want to understand the functioning of a market, you will likely need a quantitative measure of demand, and we will see that actually in the application that we look at today, that without a measure of demand, you will not be able to say much. And conversely, actually, you will be able to say a lot without actually having data on supply. Demand is really the key empirical factor in the understanding of a market. So we will come to that in the second part of today's lecture. Now, we did say, there were a couple of examples as to what you might want to understand about the functioning of the market. And if you recall the last section, the last lecture, we talked about the impact of a tax. In particular, we talked about the impact of a sugar tax, and we looked at the demand estimation in this study. Today, we will talk later in the application about a study that quantifies market power, where you go in looking at an industry and you might have an ex ante feeling about the extent of market power, and then the demand estimation and your full model gives you a concrete empirical answer as to what the market power is like in this market. All right, but before we get into that, there's quite some way that we have to take as we want to look at discrete choice models today. We've been talking about them previously, and they are part of the answer to the challenges of demand estimation. So if you recall, last time we introduced two challenges, the first one being that price might be endogenous and it might be determined partly in response to demand. And the solution that we've identified there were instrumental variables, meaning that you use cost shifters that are independent of demand in order to understand the demand at particular points of the quantity. We also talked about the second challenge, which was related goods. The challenge is that not all goods are independent. There are substitutes and complements. Hence, what happens to substitutes and complements will also have an influence on the product that we are interested in, and that gives rise to keep in consideration. So if you have J goods, for example, then you will have 9 own price elasticities to estimate, but more importantly, you will have J squared minus J cross price elasticities to calculate. So we get into a relatively large number of results that you would like to have in order to take care of this dependence to other goods. And I was mentioning that starting from utility and thereby representing a whole demand system on the basis of few parameters of utility is one way to go about taking care of related goods. And we will see this today again in the example, which looks at an industry that is very much a differentiated products industry. And there you will see how modeling demand on the basis of utility can be very useful. So again, this is going to be part of the application that we look at in the second part of today's lecture, but the remainder of this first part now, we will try to establish that. So we will take a look into discrete choice models and see, well, how do we relate utility to choice and how that relates then to demand. All right, so I'm zooming out quite a bit now that we want to talk about discrete choice models, because I think it's quite interesting to take a very general view onto that and to think about discrete choice models as one kind of model that has limited dependent variables. And you will see in a second with some examples exactly what that means. But in general, we will treat limited dependent variables by looking at a latent dependent variable, which is noted ys star, and we will say that there is this ys star, which might be a continuous variable, and that has an influence on something that we observe, which we will call ys. But ys will be observed after it has been transformed by a mapping tau, right? So there might be in the background something that determines ys, which we call ys star, but we will only see, you know, a limited amount of this ys star because we will only see ys. So we will introduce or quickly look at three mappings of tau. We will only be interested in the following in the first one, but the others I think are interesting just to understand what it means to have limited dependent variables. So the first mapping that we might want to look at is that the response that you observe is discrete, right? So you might in the background have again a variable ys star that governs the fundaments of what you observe, but you only observe whether, for example, a threshold was crossed or not. So ys is, in this example, binary. It is either 0, and that would be if ys star is below some threshold c, and it would be 1 if ys star is above a certain threshold, right? So there's a very strong transformation between ys star and ys, meaning that you basically just observe whether ys star is above a certain constant c or below. Yeah, so it's a lot of information lost in that mapping, and you only have this binary information. And we will take two steps in order to bring us from this kind of binary threshold crossing model to the kind of model that helps us estimate demand. But for the moment, let me show you two more examples of these limited dependent variables. You could have models with censoring and truncation, where, for example, ys star, the latent variable, is fully observable and is exactly equal to if it is greater than some constant c, but it might not be observed at all otherwise, right? So you would any case in which ys star turns out to be equal or below c, and that would be models with censoring and truncation. And finally, if you have models with selectivity, then the existence of reported data, which in these examples was just determined by whether ys star is above or below a constant, this itself could be modeled by the threshold crossing of another variable that governs the availability of the data, right? So in other words, you could, in the model with censoring, whether or not you observe the ys in this example, this might not depend on ys star in this sense, but it could be, you know, that you have another variable that is either 1 and makes the data available, or 0 and makes this not available. But this might be governed by some other factor, let's call it zs star. So you could basically merge these two things and have the availability itself of the data governed by something that is basically binary in determining the availability. I don't want to go down that route too far. It might be getting a little bit unclear as to how to merge that, but for you, I think it's just interesting to know that there are these models with selectivity, with censoring and truncation, but we will clearly focus on the first one, where we have a purely discrete response model. All right, so let's get to look at this in more detail. And let's zoom into this binary threshold crossing model, where we say define this latent dependent variable to be governed by a process that depends on variables xs, and this looks like a regression, meaning that we could try to understand ys star better by regressing it on a number of observable dependent variables that we have at hand, xs, and we would then, in this regression assume that there is an error that is noted at us, where f would be the CDF, the cumulative distribution function of u, so that we know the distribution of that error u. All right. Now this process of observing ys to be 1 or ys to be 0, this leads to a distribution of ys that follows the Bernoulli distribution. So basically, if ys is equal to 1, then the probability that is relevant for this to be observed, depending on the observables xs, is the probability that ys is equal to 1. And likewise, if ys is equal to 0, then of course the probability to observe that is the probability of ys equal to 0, given what xs, the observed dependent variables, are. And we can rewrite this that the probability distribution function of ys is basically the probability of ys equal to 1 to the power of ys, which is either 0 or 1, times the probability of ys equal to 1 given xs to the power of 1 minus ys. Okay, so basically this is simply saying, and I think it might be doing it in a rather seemingly complicated way. This is just saying that the distribution function of ys is equal to, well, either the probability of ys equal to 1 if ys is equal to 1, the exponent here would be 0, so the second part of the equation would not be relevant, and it would be the second part, the probability of ys equal to 0, if ys turns out to be 0, making the exponent here equal to 1 and here equal to 0. Okay. All right. Now, but more importantly than this notation, well, we want to know, well, what is the probability that ys is equal to 1 given the observables xs? And we haven't said anything about that yet. And that's where the threshold model comes in. We said that ys would be equal to 1 if the latent dependent variable that is governing this process, ys star, is greater than a constant c. Okay. Now, if we have a model for ys star, as we've written up here, then we can say something more about the probability that ys star is greater than this constant, because we can make use of the observables xs and make use of this model, and there we can basically say if ys star is equal to this right hand side, then we can say so the probability of ys equal to 1 is the probability that this expression xs times beta plus us is greater than the constant. Okay. And then we can rearrange that and say, so basically the probability is equal to the probability that the error term us is greater than the constant minus xs times beta. Right? And then we can therefore reformulate this probability as a function of the CDF of u, because here we know that, well, f gives us the probability that u is less than some particular value, and if we now want to know the probability that u is greater than some particular value, then this is equal to 1 minus f of this particular value c minus x times beta. So in that sense, thanks to the model that we have about the latent dependent variable, we can now spell out what the probability is that we observe ys to be equal to 1. So from this we can write a likelihood function, how likely is it that we observe a number of outcomes ys equal to 1 or equal to 0. Well, this likelihood function gives us this likelihood, and it's basically all the observations where ys is equal to 1 would contribute a likelihood of 1 minus f of this expression we just mentioned, and all the observations where ys is equal to 0 would give us the likelihood that is just f of this expression. Right. So here we have the likelihood function, and on the basis of that we can then estimate for a certain observed realization of ys. We can then estimate what would be the most likely parameters of this model, which is beta, such that we are observing these discrete choices 0 and 1. Maybe at this point some remarks. I'm not quite sure how familiar you are with these kind of models, but it's important to note that the distributional assumptions about this error term u, they impact the first order properties of the estimator. So they impact the consistency of your estimator, whether you will, if you have a lot of data, well, whether your estimates will converge to the true properties of what you want to estimate. So it's not only second order aspects of efficiency, like how quickly do you get to the right estimates, like with how few data points do you get some useful estimates, but it's really whether or not you get to the right estimates at all, and that is therefore indicating that the assumptions of this error term are very important. And at the same time, observing here how important this error term u is in the derivation of the likelihood function, then I guess it becomes clear and intuitive as to why the distribution of these error terms give rise to the name of the different methods that you could use, the methods that you have probably heard before. So if these errors are assumed to be normally distributed, then you have a probit estimation, and you run a probit regression in that sense. If these are distributed logistically, then you get to a logit regression. And then there are other kinds of distributions of this error that would lead you to other kinds of estimations that not necessarily have a name that identifies them. All right, so far then to basically summarize how far we've got, we have developed an idea as to what could be the process that governs ys, and if we have identified this process, how does then ys relate to some probabilities of observing, how does then ys star relate to the probability of observing ys to be 1 or to be 0? Okay, so that's kind of what we've done here, and then we've set up this likelihood function that is already very useful to make an estimation. Okay, but now if we think about where we want to go, we don't necessarily have in mind a choice that depends on whether a threshold has been crossed, but rather we think that if we have two products, well, we would choose one over the other if the utility of one would be higher than the utility of the other. Okay. Also, and that's something that we will want to have in mind and extend this to, we would like to not only look at this for two products, but we would also like to do that for more than two products. Okay, so that's where we are going now. So if you think about more than two products, we can proceed in the following way. And here I'm starting to talk about the random utility maximization model, which comes back to work by McFadden in the 70s, Nobel laureate, thanks to this work. And here we are looking at an example of M mutually exclusive and exhaustive distinct options where one discrete alternative is observed, and we want to know, well, how does that then change the process that we are looking at? So basically what we are now saying is that the observation is a choice, and ys is a choice that could be between 1 and m, and we are saying that this choice results from a maximization where we have m latent dependent variables, which is ys1 star, ys2 star, and so forth. And we are now looking at these m latent dependent variables, and we are choosing the one, for example, that has the highest ys star. Okay, and that we call this choice S. So if that were the setup, then you can think of, ys being, for example, 7, if it turns out that the latent dependent variable ys7 turns out to be higher than any of the other latent dependent variables, higher than ys1, higher than ys2, ys3, and so forth, right? So you would observe ys to be 7 if the latent dependent variable of S7 would be the highest among all possible latent dependent variables. And so this is just showing you basically how you would generalize what we've seen in two choices to a larger number of choices. And of course, you will get into a larger number of inequalities because the maximization across these latent dependent variables implies that, and meaning that there's one that is greater than all others. Okay, and that's why you have to add a number of these inequalities in order to identify which one is the largest one. I'm sorry. Okay, this then would lead also to a likelihood function. Well, I'm not sure whether this is more confusing than useful, but just to flag that you then can translate these inequalities into integrals over the PDF of your latent dependent variables ys1 to ysm, and you would integrate them depending on where these inequalities tell you the values lie, right? So for example, ys1 would be between minus infinity and ys7, because we understand that ys7 is the highest, right? So it has to be below ys7. If you look at ys7, this would be unlimited basically, but if you look at something that is higher than ys7, ys8, this would again be limited by ys7, and you would have this upper limit to your integral. So that's just to flag again that there is a way to use this setup with more than two options. All right. So now we've generalized it to more than m, and I've called it already random utility maximization model here, but let us zoom in again into the case with two choices to exactly understand how did we move from a threshold crossing to a utility maximization model. So we said that the threshold might not be the right way for us to look at discrete choice because, well, we don't have a fixed threshold that indicates, you know, ys to be 0 or 1, but rather there's a utility for product 1 and there's a utility for product 2. Okay, so if we have two choices, would it not be possible to say we have two latent dependent variables, which is basically the utility for product 1 and the utility for product 2, and then we observe a choice ys equal to 1 if the latent dependent variable, the utility of product 1, happens to be greater than the utility of product 2, which in this case would be the latent dependent variable ys2 star. And vice versa, if ys2 star would be higher than ys1 star. Ys would be indicating the choice 2. We would prefer product 2 in this case. All right. So here then we have exchanged this constant into this utility of the alternative product, and then we can go back to where we were by saying, well, when do we do this choice 1? Well, we do this choice of 1 depending on the difference between ys1 and ys2. Okay, so basically if the difference, let's call it w, is ys1 minus ys2, then we can use the model that we have of ys1 and ys2 star. We plug it in, and then, well, we get ys1 times beta 1 plus the error term epsilon 1, and we subtract x times beta 2 minus the error term epsilon 2, and then we could, you know, take this difference and call it z times gamma, for example, and look at the difference between these errors and call it u again. So we are back to where we were, and we can then say, well, we observe a choice ys equal to 1 if this ws star is greater than 0 and vice versa. Okay, so we've translated the consideration of these two latent dependent variables into one set of latent dependent variables, which is basically governed by the differences between what we have up here. All right. Now, we do recall that the threshold crossing model, for that it was very important as to what the distribution of the error term was. So here there's an interesting feature of the logistic distribution, which is if the error term epsilon that we had up here is type 1 extreme value distributed, then the error term that we have here, US, happens to be logistically distributed. Okay, so in other words, there's a way to start with these epsilons and to assume a distribution of these epsilons such that once we are looking at these differences and we reach this US error term, there is a way to have this US error term be distributed in a very familiar fashion, right? So this can be logistically distributed if these epsilon errors follow a certain distribution. So that, of course, is a very common assumption then in the literature, that the utility model that governs the latent dependent variable ys1, for example, ys1 star, this will be having an error that is type 1 extreme value distributed, so that we can assume and claim that this error US is reasonably logistically distributed. And not only is it useful for this purpose to have the difference of these two random variables be distributed logistically, furthermore, an advantage of the logistic distribution is that we are now having a closed form solution of the integral that we just saw earlier, because we can now say, well, the probability that we observe the choice f, right? So the probability that we observe y equal to s is actually equal to this fraction where we just take the exponential function of xs times beta s, and we divide it by the sum of all these exponential functions of xq times beta q over all the possible choices that we can imagine. Okay, so that would be then the probability that we observe the choice s. Now this particular expression has a number of properties. One property is, for example, that the relative odds, how likely is it that you observe choice L over choice K, this relative odds can be expressed by just the exponential function of xl times beta L divided by the exponential function of xk times beta k. So this follows the property of independence of irrelevant alternatives, because these relative odds only depend on the feature of product L and product K. So whether that's a reasonable substitution pattern, we can maybe leave that aside. But for the moment, it's just interesting to note that we are able to express this probability relatively elegantly with this term, with this fraction up here. All right, so we've made some progress. We can now talk about choices between products, where we have also modeled the utility of these products to be derived from some factors x that are relevant and contributing to this utility according to the coefficients beta. All right, now one next step to be taken is a step that, for example, can be observed in the literature in a paper by Stephen Berry in 1994. So this can be translated into a market level framework, where now the latent dependent variable is the utility of consumer I for product J, right? So this ys star is now assumed to be the utility of consumer I for product J. And interestingly, this becomes a consumer utility basically thanks to the assumed error term new ij, but the utility that can be predicted and can be estimated is a utility that is independent of the consumer I, right? So we can think of this as just a mean utility in the population for a product J, right? So then we can ask the question, if there is this mean utility that is common across consumers, does that allow us to make some statement as to what the market share of this product should be, right? And the market share function gives the probability that product J maximizes the utility for a set of parameters. So basically, the market share of a product should be related to the probability that someone chooses this product out of the entire set of available products, right? So this way you might see how knowing the probability of a choice S, for example, should translate, and thanks to this, to some assumptions in this work here, do translate into the market share of a product. Okay. I don't want to go in too much detail about the specific expressions of this integral, but just to basically say that as before, where we link the probability of choosing a certain option to a very elegant expression, here this expression as the market share function, right? So we've made a step from expressing the probability of choosing an option out of a number of options to saying that this is now the market share of a particular product, where a product might be described by its characteristics that are summarized in delta J, or basically a utility level delta J that this product generates. So it is common for these considerations in markets to require an outside option where you have N or M products, but you would also consider an outside product, which basically says that you do not purchase anything from that market of the products 1, 2, 3, 4 up to M. So here, that is being done in the next step, in the next consideration, where we say the utility level of this outside option is 0, so delta 0 is set equal to 0, and then if we think that this market share function gives us the market share for products J, then we can rearrange that to say that the log of Sj minus the log of S naught is equal to delta J. And that would basically allow us to say that the utility function delta J for product J relates to the market share of the product J and the market share of the outside option in this particular way, right? And furthermore, we can say that the utility for product J is or can be modeled by looking at the observed characteristics X times their coefficients beta, the price of product J times a coefficient alpha plus some error term that is specific to the product J. So we are basically back at an expression that can be regressed using standard regression techniques. And that is basically what we will see now in the application. We will see that this relationship is made use of for the estimation of the price elasticities and also the coefficients of various product characteristics and their influence on the probability of choice, in other words, the market share. All right, so we've made quite a long way in this first part of the lecture. So we've made it all the way from thinking about a first very simple model of discrete choice with the threshold crossing model. And now we've come to basically express and relate market shares of a product with their characteristics and price. And some of this surely at this point has been very abstract, but I hope that the example application in the second part of this lecture will make it a little bit more intuitive, and you will hopefully see more closely why this is so useful for demand estimation. So I will leave it at that. I will suggest you take a little break, which I think I might as well do, and then I will see you in the second part in just a second. Bye.